Okay, cool. Let's start. So it's lesson 8. So we finished with the random forests, and we're moving on to different methods like neural networks, or logistic regression, methods that are based on the optimizers like stochastic gradient descent. So let me go to next page. Right, yeah, so that's lesson 8. We 4 more to go. So we're almost there. I know it's a lot. Most of people do deep learning and machine learning at the same time, so it takes a lot of time. But now we should be more in line with the deep learning course, so that's good. So we're going to have the basic neural network today, and then this course cover more in detail, more in depth. So talks more about like things like regularization or normalization, something that the deep learning course doesn't talk that much. So I think it will complement that as well very nicely. You also talk more about natural language processing and also columnar data. So still a lot of stuff to do in those couple more lessons, but at least for those guys who do deep learning as well, it's more in line what we are.
Yes, totally. I mean, I think if you do this one and 9, chapter 9, I think it actually helps for what we covered off yesterday. And there were questions I had that were covered off today. So I think it's brilliant prerequisite.
Yeah, excellent. So how to run, I think we know that one. So the lesson 8, let me move that bit. Yeah, so lesson 8, we finished on lesson 7 with random forests, and although random forests are very good, there are a couple of things that random forests are not great with. So like if there is a time series component in the data, they're not that great. And also if we want to predict on something that is outside of the training data, that some data that we did not see in training, basically random forest will struggle to predict what the results should be. And with this situation, the neural networks or the regression, whether it's logistical linear regression, can help because it builds like a function and it can extrapolate and it can help predicting on the data that it did not see. And then we quickly move to recognizing, so the example for this lesson was the MNIST example, which is a bunch of handwritten digits from 0 to 9 as a database called MNIST. It's so you can download the data from the URL like this. So Jeremy showed how to get the data using a little bit of a Fast.ai library or some helper functions. So the data is stored in a pickle, Python pickle file, which then it's quite easy to load as a Python object. So we get that file, we unzip it because it gzipped, I think. Well, actually, I think pickle already know how to handle gzip. So we get that, we load that data into X and Y. So that's our training data. And also there is already validation set and a test set as well. But for this example, we don't really need the test example. So we kind of load it into underscore, which suggests we're not going to do a lot with that. But the training, X and Y, and the validation, X valid and Y valid, that's already in the pickle file. So that's quite convenient. Right, so the images are quite small. It's just 28 by 28 black and white images. However, they are not stored as images as such. Just give me a second, guys. I'm not. Sorry about that. So the images are stored as kind of like flattened. So we have the the image represented as a one row of numbers showing whether the zero is I think this image is kind of the other way around. I think the 0 should be black and the 1 should be white. Yeah, I'm not quite sure why is it like this. My understanding was always that 0 is black, like especially like in computer vision, like images like JPEG or and then 1, and then 256 was white. Yeah, so the data we get from that pickle file is 784 numbers just stored as a one row, and then we have 50,000 of training data, and I don't see it here, the validation, but I think that was a bit less than that. So then the next step before we, so once we have the data, before we can do deep, it's not deep, the neural network, we need to normalize the data. So normalization takes that data from 0 to 255 and would convert all of that. So the average for each pixel value would be 0 or around 0, and the standard deviation would be 1. So that's the normal distribution, normal standardized distribution. So this was not required for random forests, although it's needed for the neural network. So also we have to do the same for the validation set. And for the validation set, we use the standard deviation of the training set, because this is our network learned the weights based on the normalized training set. So therefore we have to use the same, let's say the standard deviation and mean to normalize the data. It's not going to be like exactly 0 for that reason, but it's close to 0 for the mean and close to 1 for standard deviation, for it's fine. Yeah, that's right. So the next step to kind of to display that as an image, and then to work with this as images in our neural network, we need to kind of reshape that flattened image. So because we know that 28 by 28 is 784, so we know that we need 28 and 28 in the last two, like in the rows by columns as an image, or by columns by rows, depends how you look at it. Then if you specify the -1 for the reshape, it's going to, is it for the reshape? Yeah, for the NumPy reshape, it's going to create as many images as it's going to find by the calculation. So that's quite helpful. We don't need to know how many images we have, although we know we have 10,000. Yeah, validation, because we're looking at validation here. So we know that we have 10,000 of those. So we could specify 10,000 here, but we're going to let Python decide based on our shape we need, and surely it's calculated 10,000. So it's quite convenient. And then we can display that image together with the validation label as, so this in this case is 3. So with that image now ready, we could start training our network. And this is just some introduction of how neural network looks like. So you have the input to your neural network on the left. So from x1, x2 to xp, that's your input nodes, input layer. And at the end, you have your output layer, which is, I don't know why it shows this kind of line here. And then everything in between input and output is your layers of your network, also called hidden layers. And you can have many of those hidden layers. In this example, we're just using the one layer. So the network normally consists of the linear function, which is your input multiplied by the weight. So the W11 or I1J, 1I, K, so on. And that's going to give you an activation. And then we're going to use nonlinear function because the combination of the linear function and nonlinear function, when you have like more layers, it's going to give you ability to approximate like any other function. So that's quite useful feature of the neural networks. Very powerful feature, actually. So to do that, we're going to use, at least that's what Jeremy used in this example, was the PiTorch. So initially importing the torch NN as NN. That's kind of similar standard as pandas, PD, and so on. So usually that's how it works. That's how people import PiTorch.
So just, Mikhail, a quick question for you, or for anyone in general. I've missed some parts of this. So is there a really good reason why we're using PiTorch versus Keras? Yeah,
so at least what Jeremy says. So they used the TensorFlow and Keras for the first version of the course, and then the second one, I mean deep learning, talking deep learning. So that's what they've used, and then they switched to PiTorch. And the reason they told was that the PiTorch provides this dynamic graphs, some features that TensorFlow does not provide. So there's some things they can do a lot easier and faster using PiTorch. I know that's a high-level overview.
Also, the new Fast.ai version 1 library on top of PiTorch.
Yeah.
Exactly. Yeah, but why PiTorch versus any of the other ones out there? I know they did Keras a long time ago, and I just didn't know why.
Yeah. So yeah, that's right. So they what Jeremy said, that there's some things they could not do in TensorFlow and Keras, and so they decided to switch to PiTorch, and they've created the library to make it a lot easier than if it was, especially like for neural networks. There's one lesson that in deep learning, the version 2, Jeremy shows how to do stuff with Fast.ai and PiTorch, and then he shows how to do this exactly the same, say like neural network in TensorFlow and Keras, and it takes you much more lines of code, and the result you get is not as good as what they have. So that was one of the reasons they decided to switch. They wanted to make it better, which TensorFlow were not allowing them to do, and not that flexible, to what I understand. And then the Keras, although it's easier than the plain TensorFlow, still not the level of easy that they wanted to achieve. So I think that's why they decided to create to change to PiTorch and Fast.ai as a library.
Okay, great, thank you.
That's what I've heard. Yeah. Anyone's got different opinion on that?
I remember that they were talking about debugging, that with PiTorch it was easier. I never tried PiTorch, so I have worked all with Keras. But okay. I remember Jeremy saying that it was easier to debug because you don't have to make a graph, and once you finish, you can run it. Something like that is the only thing I remember him comparing both.
Yeah, and I think as you mentioned, I think the big bonus for PiTorch was always the dynamic graph. I think I don't really know the details, but apparently TensorFlow is now also including some kind of a dynamic feature in the newest versions, because they were obviously missing it. But in principle, it's a compiled graph in TensorFlow, and totally dynamic in PiTorch, and therefore much more for the advanced stuff.
TensorFlow is catching up with PiTorch from that standpoint, and the latest release has that kind of dynamic graph feature. I was trying to figure out what that was called, but yeah, that's.
I think it's eager, right? It's eager, I think, something like that.
Eager execution.
Yeah, that's right. And also PiTorch is trying to catch up with TensorFlow like in production, but I think it's good when they compete in that way. All right.
Yeah, eager execution is the word I was looking for.
Yeah. Yeah. So who knows? Maybe the next version of the course will be something different. I think that was another kind of Jeremy's comment that we shouldn't really spend that much time. You know, I think we should spend that time learning the library, but we should be aware that it may change in the future, in the near future, especially with the progress in deep learning, machine learning that's going on now. Yeah, so in this case, after importing PiTorch as torch, the simple network that Jeremy defined is using the sequential. That's a function. That's a method from Torch, and you can define your network. In this case, it's just two layers: the linear layer of the size 28 by 28 and 10, because we need our 10 digits from 0 to 9. It's 10, and the next layer is the nonlinear layer. In this case, the log softmax. And then he puts all of that on a GPU by adding .CUDA. Yeah, so the first layer is 28 by 28, because this is the number of, this is the number of pixels per image. And the output is the 10 classes. And then the softmax. So the other, there are different nonlinear layers. Of course, you can define. In this case, the softmax was chosen because we want just one, per each image, we want just one label. And softmax is going to give us a prediction where one label is going to be have the biggest prediction number. In some situations, you want to have multiple labels per image. So like if you just picture of your room, you would say there's a chair, there's a table, there's a picture there. So there will be like multiple labels, but in this case, this is just basic one label per image. And the softmax is the good nonlinear layer and the last layer as well, because in this case, we only have one layer as such. So that nonlinear layer is also the last layer, and the softmax is designed for that. So once we have our network, our data, then the next step is to kind of like bind that data together using that's Fast.ai library, image classification data, and in this case from arrays. So we show which Python arrays or NumPy arrays you want to use as our training. So the X and Y, that's the training, and the validation is X valid and Y valid. So, and the image classifier from data is going to make that data available for the Torch model to use. That's right. So that's what this slide shows. And the next couple of things we need to define before we can start training is what sort of loss function we want to use. So the loss function is going to tell the model whether with the changing of the weights, whether we improving with the model or it gets worse. So in this case, we're going to use the cross entropy, which is called NLL loss as well. And the matrix is something we're going to print with which each epoch run. So in this case, we want to see accuracy, how many digits we've predicted correctly. And also the optimization, we need to choose what sort of optimization, like for example, stochastic gradient descent, or in this case, the Adam optimizer was chosen. Okay. So once we have that, we could run the fit method. And then we put as arguments, we put our network we've defined as net. We put our data that we've made available, MD. We define how many epochs we want to run. So how many times we want the network is going to see each image. So if we say 1, the network is going to see each image just once. The criticality, I think, needs the same as loss. And then optimizer, or our optimization method and the metrics. And then once we run that, we're going to get the results. So 0 is the first epoch, and the first number is your training loss, so 0.31. And the next one is the validation loss, 0.28, and the accuracy 0.91. So the model with just one layer gives us, with just one epoch, gives us accuracy of 91%, which is, I guess it's not the best, but I think it's quite good already. So if you want to use now the predictions, we would get the, well, in this case, we just use the validation data set for that. He's not using the test set. So he gets the predictions, and this gives you, this gives him the array of 10,000 and per 10. So now to get, because so it gives like 10 predictions per each image. It gives, so then we have to select the highest number out of those predictions. So like in this case, if we look at prediction of the one row, I guess, we get different numbers for different digits. So we have to find out the highest number here. So for that, we use the argmax. And then the argmax give us the location of the highest prediction. And based on that, we can find out whether that was 0, 1, 2, 3 or something. And then we created, so with our predictions and the validation, because we know the predictions for validation set, we can calculate as well, like manually, our accuracy, which is the same as the one that was created by the neural network. And then again, we can plot those images.
And I think the interesting part of that is that these numbers that you took the maximum of, these are the log probability, so that if you wanted to know like how confident you are that your digit is a 7, for example, you can look at the probability, because it's gonna compute under the hood. It's going to compute the 10 probabilities for each digit, and then you take the maximum, the digit that has the maximum probability is the one you label it with.
Yeah, you're right, because this is like -10, so that will be not so good probability, right? Yeah, makes sense. Yeah. And then as a last thing, what Jeremy showed this lesson was how you could define your own logistic, because that's basically one neural network with one layer is the same as logistic regression. So it just showed how you could define logistic regression yourself using nn.module class. So you're going to create like subclass of that class. And this gives you the same results. So there are a couple of ways you can do the same thing. And I didn't play with those in code as such, but this was pretty much this for that lesson.
Yeah, can you flip back? I mean, that's basically, I think, the nature of the PiTorch models, right? So you basically can stack them as you like. You always derive from any module, and then if you do that, you already get all the benefits, like the backprop probability stuff included, and you just have to adhere to some protocol that you have to have a forward function basically defined, and then you can do whatever you want, and it's all compatible. But we don't do that because we just use existing modules anyway, right? So, but if you want to do something really custom, you can just build it like that and then just plug whatever into forward, and then you have your custom module that can be chained in the sequential kind of thing, and then you can build up whatever kind of model you want.
And in that forward function, you can see where they're computing the probabilities. It's the it's the third line where it says x, e to the x over 1 plus e to the x. That's the probability. That gives you the 10 different probabilities.
Mm-hmm.
Yeah.
So just a question around this forward. Where because he's mentioned it before. Where is forward actually called? Why do you go from
by PiTorch then, like, or Fast.ai on behalf of PiTorch? Is basically when you do the forward run in the model, this one will be executed, and therefore you have to have it. Otherwise, it's not compatible. Like in training, you always have a forward and a backward pass, right? And in the forward, you basically calculate you multiply your weights with your training data and go towards the end of your network. And once you're there, you're basically back propagating to update the weights. And that should be the forward step here. And the back prop is automatically done because PiTorch can automatically differentiate. So that's done for you. So you don't have to, because every variable or every tensor has the option to be an autograd. And therefore, if it's enabled, then PiTorch will keep track of it and can do the back propagation. So you only have to customize the forward if you want to. Does that answer that? Or?
Yeah, thank you.
Okay.
Yeah, there's a question in the chat about if we have an imbalanced data set, which metric other than accuracy should be using?
Again, if it's unbalanced?
Yeah, if you have select more 9s than 3s, for example, and a lot more.
I think that was asked in the forums in the deep learning one. I think you either do it in your pre-processing, that you do oversampling, that you kind of balance the classes by sampling that are less frequent by having them sampled more often, or you provide sampling weights into the model like that certain have a higher weight. I don't think it's included in Fast.ai, if I remember yet.
Yeah, so
you don't have this option of providing weights.
Yeah, you would not change the accuracy. You would not change the metric. You would basically generate some more either images from the class or sample more maybe from that class.
Yeah, so I don't understand where the question about why does accuracy come into play there, because it's not about the metric, right? It's more about making sure you have a balanced class.
Accuracy is purely for visual inspection. It doesn't affect the model training or performance at all. It's only reporting as a number, so it's not interacting with the model performance. It's just showing the model performance. That's why you're free to change it to whatever, like, it doesn't matter. It's just wise to choose one which informs you the most.
Okay. Yeah, so basically that's and from like a quick lecture recap, and we already talked a little bit about those topics, but so is there anything else that you guys found interesting or confusing or?
Yeah, I do have a question actually, because I was just able to squeeze in this thing literally about half an hour before this started. One of the things he mentioned was this Chi-Ming-He initialization, where you divide the torch random number dimensions by dimension 0. I'm going to look it up, but can someone provide like a high level view of what that's about?
Yeah, he very briefly mentioned that, and he started typing that in the browser, but he stopped quickly. I didn't look into that myself.
I can't explain it either. I know that it's a better initialization, but I forgot why that was.
We could look at that quickly. If anyone remembers or know how to spell that. What did he say? Is that
So it's K-A-I Ming H-E initialization.
Initialization of deep layer, okay. Some here, there's a PDF on that. Maybe not the PDF we want, okay.
I forget the name wrong, it's not. Oh yeah, it is kind of.
Not sure if that's about initialization. Oh yeah, there's something here. Doesn't talk a lot here about this. At least this is the right side, I guess. Is there a list of topics? There's normalization. No, I cannot see it just now. There's a lot of stuff here.
I'll tell you what, I'll look it up, and before next Sunday, I'll put a short document of what I've figured out or what I've understood from it.
Okay, excellent. That'll be great. Thank you. Okay. Where is it? Yeah, so we already said there are a couple of us doing a couple of things at the same time. So that's kind of, for me, the stumbling blocks, kind of the issue there. It's a lot of material to cover, especially he talks a lot of stuff in deep learning, the image recognition, natural language processing, collaborative systems, like everything. And so that's a bit of a challenge there. Is there anything that you've learned or find interesting in this lecture?
No, I think it's just that if anyone missed it at the start of the conversation, this is a really good help to the deep learning course. So, recommend listening to this and next week's one, and it'll help with the course 3.
Yeah, indeed, it's should complement this very well. You guys doing anything interesting for homework or any side projects? Initially, we're talking here about some Kaggle competitions. We've entered like taxi competition. So now we're talking image recognition. So there's a lot of Kaggle competitions on the image classification or segmentation, or this is quite a lot of image. You guys doing anything on?
I've been just trying to follow the 2 courses, and I keep seeing all these new Kaggle competitions pop up and think, oh, this might be nice to try, but then I just don't have time because I'm just trying to follow the class right now.
Yeah, it's the same for me. I mean, they only run for like 2 or 3 months, right? And if you jump in and really need to learn from scratch, it's almost too late to at least for the live ones. I kind of skip that for now and just look for interesting old competitions and see if there's a data set that I like.
Yeah.
I did do one thing that from last class. Someone was asking about the standard deviation formula that Jeremy used, and so I I wrote up a little thing on it, and I posted it on the forum for this, I think for lesson 7. And for most of you, it's probably too much, because you probably already know it, but I think some people really wanted to understand how that formula came about, so I just wrote up a thing about it. There's a link on the Slack, on our Slack channel.
Would you like to give like a 5-minute presentation on that topic?
Sure. I mean, let me get the Slack channel link, and then I'll go to it and share my screen.
Yeah, thank you.
Okay, so here we go. Okay, I'm going to, I think I'm going to share my screen, and then find it. Okay, so it says I'm sharing my screen, but someone has to give up sharing their screen before I can share mine.
Yeah. Okay. Let me. Oh, stop share. Okay.
Okay. Here goes. This is it. Okay. Are people seeing this?
Yep.
Okay. So there's just a little. It's kind of like a trivial little formula that Jeremy uses to get a faster version than just the if you computed the standard deviation from the first formula that I showed there, then you're going to have to compute. It's not vectorized. It's kind of, you have to do a loop and get through it, so it's a little slower. So there's a well-known formula that I'll just skip to the bottom. There's a well-known formula that people use for this, where it's this formula here, where the standard deviation is the square root of the mean of the squares minus the square of the means. And that's the formula that I just went through the derivation of it, and then I showed how Jeremy implemented it in code, because he defined a function over here, and this is basically the implementation of this formula. So I mean, most people aren't going to want to go through all this, but I just thought I would sort of go through and derive it for people. And it in here, if you're not familiar with these angle brackets, I explain what they mean. They're basically, when you put angle brackets around a vector, that's it's the expectation, called the expectation value. And if all the weights are uniform, then it's the same as the mean. In other words, if the distribution of x is uniform, then the expectation value is the same as the mean. So I just go through that notation because Jeremy used that and without explaining it. So I thought I'd just go through it and explain it so people can follow it.
Cool.
So if interested, you can delve into that. Otherwise, it's basically just this formula down at the bottom here that that Jeremy used for standard deviation.
Nice. Thank you.
That's it.
Thank you.
Okay, I'll relinquish my screen.
Since we're talking about what people are doing, like project-wise, I think is also interesting. Like I find new stuff each day, I guess. But, there's a forest classification. I think it was mentioned in the forum somewhere as well. Like a simple classification thing that I might try to compare the random forests to the tabular one. So if anyone else is interested, in addition to the taxi one, which I still want to write up, but I will afterwards probably have a look at this forest classification from USGS, I think, the data, and that looks kind of neat and small and manageable.
Sounds great.
For the learning, I mean, I don't know about you guys, but whoever is doing the deep learning one as well, I find that I hop around too much. It's just so much stuff I want to do, and it's just too hard to focus and be in time to doing that, because I thought, okay, the NLP stuff is like super cool, but there's so much involved there if you don't really stick to the example to the point, then it kind of blew up in my face. So
yeah, but I think that by going through these examples in class, it's frustrating for me to not be able to go out and do Kaggle things and challenges and so on. But I think that by concentrating on learning these tools, now I feel like if I had to do a Kaggle competition, I have some place to start. I would have all of these tools that Jeremy.
Yeah, for sure.
And so it's good. I think it's going to be fine. I think eventually when I'm done with these classes, or maybe even before, I'll jump into a Kaggle competition and have some fun.
Yeah, I'm not doing any Kaggle competition at the moment either. I'm just looking for data that kind of might be similar to a problem tackled in class, and I just do it with a different data set because because it's more exciting than just doing the exact same thing and follow the notebook guys.
Yeah, once we finish all those courses, end of the year, there'll be more time, unless we start another study group on reinforcement learning. There's already talk on the Slack about this. So whoever is interested in reinforcement learning, Sam is looking to start study group sometime next year.
Yeah, I'm a sucker for that kind of stuff, so I'll jump in. But somebody mentioned this class on Udacity, which is a free course in PiTorch. So now I want to look into that too, and it's kind of too many things.
Yeah, indeed, it's.
Can I get a kind of a hands up? Who's like evaluating Keras, TensorFlow, and PiTorch at the same time, or are you kind of focusing more on PiTorch now? Because for me, I don't know, I'm a bit drawn. I mean, all the actual jobs and stuff, they are more for TensorFlow really, and PiTorch seems to be totally academia. Are you kind of just learning the concepts and don't care like which framework you learn, or is it that you already know TensorFlow kind of bit, or?
No, I took the.
Just wondering.
This is just me. I took the Andrew Ng's specialization where in AI where he uses TensorFlow and Keras, but you really don't get much unless you do a lot of extra work. It just goes by so fast.
Yeah, I did that too. Yeah,
I don't feel like I really got a good understanding of TensorFlow and Keras, just a basic working knowledge of it. And so for now, I'm learning PiTorch, and then eventually I'll try to learn all three and, find out which one is better for which projects and so on.
Okay.
Yeah, I'm only PiTorch for now. I didn't really spend any time with like learning TensorFlow.
Yeah, that's what I thought recently, right? I mean, ideally I would want to know both, but seems like Fast.ai gets you to a result really quick, and it's probably worthwhile to really dig into PiTorch and just get familiar with that kind of thing, right? Instead of juggling something.
Keras is very similar. You basically build the network layer by layer. I think in PiTorch you have it all. It's all under the hood. You don't have to actually pay attention to the layers. It's just done for you. If you want, you can look into it. But in Keras, you actually build the network layer by layer. You build.
Yeah, I did some small project with it. Yeah.
Yeah, and it's nicer because you sort of have your hands on it more. You get a better understanding of a better working knowledge of what a neural network is and so on. But you can get the same thing by just delving into the hood in PiTorch, just looking at the definition of the model. Like you can do DIR. When you build a model like Learn or whatever, and you go DIR of Learn, and then it shows you all the layers underneath and so on. You can see it.
Yeah, so I looked at Keras about a year ago, and getting as far as creating models and all was really easy. I just couldn't find enough resources to help me figure out how to get past things like image augmentation or when you're trying to transfer learning and so on. They're just, well, at the time that I looked at it, which was, I think over a year ago, I was struggling to get beyond the simple stuff. And that's when I kind of abandoned my look at Keras, but I'll probably go back to that. I don't know, what's been your experience?
They're kind of similar for me, to be honest. I did some follow some. For me, it's always like, okay, if you just follow some tutorials or whatever, it all makes sense and it's all laid out and all kind of works. But that's why I also want to apply my own data sets or whatever, because that's when it normally falls apart. Like for me, right? If you just follow a notebook, an existing one, then it's all nice and dandy. But when you bring your own data, that's suddenly a bit different or whatever, and suddenly, yeah, this knowledge doesn't really help you that much, right? You really need to understand the stuff to then progress. So I don't know, but yeah. Don't know.
Yeah, but I also agree on Christian's point about TensorFlow being used in production a lot. I guess if you apply for like jobs, people would use TensorFlow more. So it's a kind of a good question about whether you actually need to learn TensorFlow, or are you good with only PiTorch? It's a good question.
Yeah, I thought about actually trying to, like, when I have a neat small project really wrapped up, just re-implement it with Keras TensorFlow and so.
So on the topic of TensorFlow, is there any resources anyone has tried that they can recommend for that?
If you want to just jump right in, I mean, they have this. Google has these classes in using TensorFlow on Google Cloud Platform. There's like a specialization in that. Yeah, and it's pretty much total immersion. And I think that they just put these classes out and they really haven't worked out. I think they'll be good when they do.
I mean, if you want to learn the Keras kind of thing, then I guess the book of what's his name, the French guy, Keras developer. That's
Cholet,
really,
Francois Cholet.
Francois Cholet.
Yeah, that's supposed to be really good.
Yeah, I was watching that book on Amazon, and it all of a sudden dropped down to $15, and I should have bought it, but I didn't, and then it went back up to $29.
Okay.
I have it and I read it. It's nice. But it's about Keras. So I was going to ask, if you have used TensorFlow and Keras, is there any reason to use TensorFlow? I mean, with Keras, you can do more or less everything, and TensorFlow is really like low level, no? You have to do many things just to build a neural network. Instead, in Keras, you can just write a couple of lines and you have it. And if you want something more,
similar like Fast.ai, right? It's kind of nice and better wrapper, but I guess, at least to my understanding, in Fast.ai, you get the kind of benefit of having Jeremy's like opinionated selection of stuff. So you get like not 5 choices, but the best choice by his definition for NLP at the moment or whatever, right? So you get a nicer, cleaner interface, but also probably like state-of-the-art algorithms beneath or networks beneath.
With Fast.ai, I didn't try to do anything fancy, but once with Keras, I was building a fast RCNN or something, so I was doing something else, and I used the functional API, which allows you to build a bit whatever you want. It's not just like a stacked network. I think that with Keras, you can do more or less everything. I never have seen the need to use TensorFlow. You know what I mean?
Yeah, actually, I went to a couple of meetups here, and there's a guy who's really like experienced in stuff, and he was, I don't know, building his own networks before TensorFlow and everything, and he's doing everything in Keras now as well. Like apparently, it's flexible enough for really professionals as well. I was just wondering, like, since you seem to have done quite a bit with Keras and TensorFlow, what's your thinking on Fast.ai PiTorch at the moment? Like, apart from being allegedly more flexible, like do you like any of them better, or do you feel like one has a big advantage over the other for the stuff that you do? Or
in my case, I haven't used PiTorch yet. I mean, I have followed the course, only the machine learning. I tried to start with the deep learning like you guys, but I couldn't do it. The two things was too much. So
everyone's doing everything.
Yeah, so I want to learn PiTorch and to try the things in PiTorch, but so far I have used Keras only. And I'm happy with it, but I'm really curious because, for example, this thing with the debugging, at some point Jeremy mentioned that it's easier to understand in PiTorch because it tells you better where it's failing. Instead, in Keras, you get some cryptic thing that sometimes is really hard to, find out where the network broke.
Mm-hmm.
I think what's the TensorFlow, they got this Tenderboard, right?
Yeah, but I think there's something coming up for PiTorch now as well. This
Yeah, I think I saw something as well.
Tenderboard X or something, or
the Tenderboard is like a visual representation. I don't see it now. TensorFlow. Oh, TensorFlow.
Tenderboard.
Yeah, that's right.
And I think for PiTorch it's Tenderboard X or something.
Where you can see it. Yeah, basically gives you like a graphs and things. You can just change some settings and see how that would improve or affect your model. I didn't use that, but that seems to be quite a nice tool. And indeed, I did also saw, and I think I posted that on the forum, on the Slack, that someone created something similar for PiTorch.
Yeah, I put it in the chat.
Oh, you also did? Okay.
So just now it's Tenderboard X.
Yeah.
But I never used it. I'm not sure if it's just hooks or bindings to actually use Tenderboard with. See, it looks like it, like visually, it looks like to be Tenderboard.
Yeah. Yeah, that could be interesting. Yeah, so basically it gives you like a nice, nice board so you can change things and see quickly visually how that, that seems like a nice tool. Interesting.
Anyone used that yet? No.
Didn't. So I'm trying some Kaggle competitions. Like there's this quick draw competition, which has got a lot of so Kaggle. Let me see if I can find it quickly. No, let me go that way. So there's the data set is huge. So that's 50 million of drawings like that. So quick draw is like a Google site when you have like 20 seconds to draw something they tell you to draw. And then they take that image and put that in the database. And then they made those 50 millions of those drawings available. And you have to predict what they are based on the training data. And the issue here is that there's a lot of those images, so it's quite difficult to kind of compute all of that. And the other issue with that is that some labels are basically incorrect. So because, for example, the application, which is like quick draw, so when the application tells you to draw a wheel, I can draw and I can leave that, and then I believe that application will take that square and assign the label of wheel to that, and then that's a noise in the all. Yeah, so the timer's up. It didn't guess it, but to my understanding, that square would now go into database as wheel, and then you get in your training data, you get like about guys estimated about 10% of incorrect labels. So what the guys are trying to do, they're trying to make a batch size as large as possible. So then those noisy images, they kind of like averaged out. So then you kind of reduce the impact of that noise. So that's what.
Also, so meaning that if you had a large enough batch and you said wheel, then hopefully there'd be a whole load of other wheels to tell you that okay, that's probably not a wheel.
Yeah, that's what the kind of, at least on the discussion on the Kaggle forums, that's what people are trying to do to overcome that issue. So they're trying to use as large as possible batch size, like 600, if not more. They're trying to use all the 50 million images, which takes forever to train. So it's kind of, I guess, still not the real life example, but still some sort of kind of like a challenge where you have to deal with that big amount of data. So either you can take a subsample of that, start with, even train you with just 1% of the data gives you already like 90% accuracy. But like to get more, I think you have to really train like with all of them and with large batch size. And then the data they give you, it's not image actually, it's a vectors. So when people draw those things, it stores that as vectors, like from A to B, and then again. So they give you vectors, but some guys made some kernels available that takes those vectors and convert that into image. So your input to your network will be an image again. But some people try even like the LSTM networks for that and try to see the patterns in those lines, in the strokes. So there are a couple of different methods people tried. I think like doing competition, you can see all that stuff going on, and you can learn also a lot from the forums, what people do there as well.
In this competition, if in the test data, it's possible that you have also something wrongly labeled, or maybe those are checked, because you cannot guess, no, what it is. If you never saw it before and it's wrong, you cannot guess it, I guess.
Yeah, on the test, yeah, good question. Because on the test set we don't know, we only have the images without labels.
So because these questions come from thinking that maybe it will be good to do something to pre-filter the images, no? So for example, you take one class and you do, I don't know how, but you can do some sort of clustering and you remove the farthest examples from the, from the mass of, the ones that are closer between them or something like that. I don't know, just thinking.
Yeah, that's a good point. So if there was like a way to do it, that would be great. So to get rid of those wrongly classified labels. But for me, I'm so like all those images like on this page, B's, every single one looks so different. You know what I mean?
Yeah, that's true.
It's like, I'm so surprised that neural networks can make sense out of it. It's like unbelievable, but in fact it can, but it's crazy. All right, so we are 1 o'clock. I guess that will be for this meetup.
So, Mikhail, I do have just one question. It's around the random forest implementation. Is the, and I'm still catching up on some of the videos, is the Fast.ai random forest implementation vastly different from the scikit-learn one? And is that what he's talking about, and how it's different and what the advantages are?
Well, he's using the scikit-learn random forest. The only Fast.ai library he uses is for like to prepare the data for the scikit-learn random forest and stuff like around the regression model is just scikit-learn.
Yeah, he mentioned in one of the lectures that basically the scikit-learn one is just much more optimized. So even though he's coding it up now in the course, and you get some pretty decent performance, even especially if you introduce the Cython language stuff, then you can get close to scikit-learn, but it's nothing different or whatever. He's just showing that it's not magic basically, and that
Great.
You can program it yourself. But in the end, scikit-learn, you just use that one.
Okay, excellent. Thank you.
Yeah.
Any more questions before we finish for the day?
Yeah, did he talk about gradient boosting in lecture 8? I thought he talked a little. No. Okay.
No.
Okay.
Yeah,
yes.
I don't think it's coming up either. I think I kind of ran through the coming lessons like briefly, and I don't think there's anything about gradient boosting.
Yeah. So indeed, he chose random forests, I believe, due to it's easier to interpret, maybe easier to teach, I guess, easier to compute, and it still gives you quite decent prediction. But he indeed, in one of the lectures, he mentioned that this is the kind of random forest together with other the tree-based methods like XGBoost or the light GBM. These are the methods to to learn for this purpose. And like if you look at Kaggle now, everything is like almost like XGBoost or the light GBM. No one is using random forests for that, for those problems. Okay, excellent. So next week we have lesson 9. And that's going to be, I forgot what that's going to be, but it's going to be something interesting again, I guess. Cool.
I think you're going to do SGD, stochastic gradient descent applied to the same, well, maybe no. No, that's this one. I'm sorry. That's this one.
Yeah, we'll find out. It's always interesting from German, so it's, I'm sure it's nice. Once again, if you want to do any mini presentation, 5 minutes to talk about something, just let us know, and we'll do that. Okay.
Okay, thanks, Michael.
Thank you very much.
Bye.
Thank you. Bye.
Thanks, Michael. Great job.